Transonic flow over a symmetric double. Wedged airfoil. Abstract pressure distribution over an airfoil is an important consideration to ensure good performance of the aircraft. In the present work, a double wedge airfoil present in a wind tunnel is considered and simulated at transonic speeds for a given angle of attack to find the variation of coefficient of pressure using ANSYS 18.1. Keywords: transonic, airfoil, coefficient of pressure. Introduction: pressure distribution over an airfoil is responsible for lift produced by the airfoil. The objective of this experiment was to find the variation of coefficient of pressure over a symmetrical double-wedged airfoil. This analysis involves a two-dimensional double-wedged airfoil model with a half-wedge angle of 4.5 degrees and a chord length of 12.7 cm. The angle of attack chosen is 2 degrees and the flow Mach number is 1.002. Experimental results provided in 1/4 pressure distribution over a double wedge airfoil are compared with result obtained through simulation. Dimensionless number which describes the relative pressure throughout the flow field is known as the coefficient of pressure. Modeling: Figure 1 shows the geometry of the symmetric double wedge airfoil. Figure 2 shows the position of the airfoil with respect to the wind tunnel. Meshing: the model was designed using the inbuilt design modeler present in ANSYS workbench. Meshing the 2D geometry was performed by providing edge sizing to the 4 edges of the airfoil with no biasing. Inflation is also provided by choosing the boundary as the sides of the airfoil. Figure 3 shows the final mesh obtained. The named selections are the inlet, outlet, top wall, and bottom wall of the wind tunnel as shown in Figure 4. Solver setup. The type of solver used is pressure-based solver. Ideal gas equation was used for the properties of air. Using pressure far field with Mach number 1.002 at inlet boundary conditions are provided. Calculations were performed for 10,000 iterations and it was observed that the residuals became constant, horizontal line, hence it was concluded that the solution was converged as shown in Figure 5. Results and discussions. Plot of coefficient of pressure, Cp, against chord of airfoil, x/c, for both top and bottom surface of airfoil is obtained from simulation and compared with graph which is experimentally obtained, one as shown in Figure 6. There is close resemblance between experimental and values obtained from simulation. Coefficient of pressure decreases and suddenly increases at the middle section of the airfoil. Y and values obtained is as close to 1 as possible along the top and bottom walls of the airfoil as shown in Figure 7. Conclusion: the pressure distribution over a double wedge airfoil inside a wind tunnel at an angle of attack of 2 degrees and a Mach number of 1.002 is obtained, and it is observed that the coefficient of pressure increases suddenly at the middle of the airfoil.